Hey everyone, welcome to this explainer. Fellow developers, system architects, you know the drill. If you've ever tried to keep a complex, autonomous agent from just completely spinning out of control during a really long-running execution, you know exactly how chaotic things can get. I mean, we're talking nightmare scenarios, right? Like an agent silently deleting a production database all because it hallucinated a success state? Nobody wants that. Today, we are taking a deep dive into the architecture of Sakshi. I'm going to walk you through our exact blueprint for why building a deterministic dependency-light monitoring substrate isn't just a nice-to-have anymore. It is absolutely crucial for real agent stability. We're going to look at the exact design choices that took this system from just a basic runtime to a highly robust, typed monitoring substrate.
Okay, let's dive into this. This is our foundational concept, the witness pattern. As lead architects, we had to establish a core philosophy before writing even a single line of code. A witness is basically a watcher. It observes the agent's plan execution, evaluates those actions against our declared expectations, and it steers the agent's cognition. But notice that crucial second half of the definition there. It does all of this without actually doing the cognition itself. This strict separation of concerns, that is the foundational blueprint of our entire system design. The agent thinks, the witness watches.
So, here is our technical roadmap for the explainer today. We'll start with the paradigm, move into the foundation, then look at the escalation, the defense, and finally wrap up with the architecture's core.
Starting off with Section 1, the paradigm deterministic by design.
And this brilliantly illustrates our very first major architectural choice. We deliberately, aggressively even, rejected heavy monitoring systems. The typical industry approach right now is just throwing more machine learning at the problem to monitor the machine learning. But think about it. That introduces untyped logic, massive hallucination risks, and totally muddied signals. You are literally fighting chaos with more chaos. It's like asking a hallucinating intern to grade their own exam. Now consider our alternative, the Sakshi paradigm, a deterministic substrate. We rely on strict type seams, queryable streams, and stable contracts. Because when an agent fails, you don't want a black box guessing game. You want a stack trace and a queryable log.
I really want you to hear this quote directly from the architecture documentation. The package imports no host runtime, no fast API, no graph database, no machine learning framework. This was a deliberate, incredibly strict design choice from the architecture team. We needed to keep the library small and completely dependency light. The host application supplies the concrete services, and Sakshi? It just exposes the type seams. This means the substrate remains purely deterministic. It's incredibly fast, it's totally auditable, and it doesn't drag a massive bloated ecosystem of dependencies into your clean host app.
All right, moving to Section 2, the foundation. Type seams for stability.
Let's look at exactly how we built out version 0.4. When an anomaly hits your system, how do you actually track the fix? Well, we created a discrepancy resolution data transfer object, a DTO, that elegantly captures the whole chain. It starts from the symptom, moves to the explanation, defines the new goal, and outputs the plan. And what's just beautiful from an engineering perspective is that this single shape works end-to-end at both the object level and the meta level, completely by design. It's a clean typed stream, not just some scattered emission of random logs.
And to route those explanations, version 0.6 introduced this incredibly developer-friendly routing table, the TRAP taxonomy. That stands for transparency, reasoning, adaptation, and perception. Instead of relying on fuzzy, unpredictable keyword matching, every single failure mode gets tagged explicitly. If the failure happens on the reasoning axis, the deterministic recommended action is to swap the module. If it's perception, you strengthen the signal. We completely replaced black box guessing with explicit, typed axes.
Let's jump into Section 3, the escalation, evolving the substrate.
Let's move to and see how this builds over time. Once we had those simple typed seams in place in 0.4, we escalated rapidly into some highly advanced self-monitoring capabilities. Release 0.5 gave us metacognitive module contracts. Release 0.7 introduced two-axis trust calibration. And by release 0.9, we were implementing hard defensive guards. Each release sequentially added strict deterministic interfaces to wrangle agent behavior, and we did it without ever compromising that dependency-light footprint we talked about.
I gotta say, one of my favorite pragmatic solutions from the 0.5 release is canalization metrics. If you've ever run autonomous agents, you definitely know the dreaded stuck loop. You know, where the agent is endlessly refreshing a broken API, completely convinced it's working hard, while the actual world state hasn't changed at all. To stop this chaotic failure mode, we introduced a frozen struct that tracks depth, dwell time, and perturbation resistance. The host can then deterministically route based on the wristband, widen the search, swap a module, or just escalate the whole thing to a human.
Then, in Release 0.7, we tackled the massive problem of trust. When an agent says, "Hey, I am 90% confident," what does that actually mean? We created a trust bifurcation DTO that splits trust into two distinct handles. First up is competence confidence. How reliable is the agent's actual capability to do the task? And second is integrity confidence. How much do we actually trust the signal pipeline reporting the data? By separating these into specific typed handles, an agent can no longer hide a completely busted signal pipeline behind a high capability score. Both axes absolutely must hold up.
We also realized we needed a way to handle intrinsic motivation, because that can quickly lead an agent totally off script. Enter the creativity envelope. This is a pure function that bounds the agent's motivation system. It strictly declares forbidden attributes, forbidden motivation types, and a maximum novelty score. The system never actually generates motivation itself. It simply uses this envelope to bound and audit the host's intrinsic impulses. It's a pure, deterministic gatekeeper for agent creativity.
Moving into Section 4, the defense, halting hallucinations.
This brings us to the real climax of the 0.9 release, where we implemented hard-typed protections against catastrophic agent drift. I really want to pose this vital engineering question to everyone watching, because it is the classic failure mode of autonomous systems. How do we prevent agents from hallucinating success? Seriously, how do we stop an agent from just writing a log that says "goal achieved" when it actually did absolutely nothing out there in the real world?
Well, our answer is the Reward Integrity Guard. This protocol strictly forces the system to validate any goal achievement claims against exogenous evidence keys. We are talking about hard external data, an actual database commit, a real sensor reading, a completed tool call. If the minimum required evidence keys are not present, the guard explicitly refuses the success claim with a typed reason. The agent literally cannot silently declare victory without the actual world having moved.
And working hand in hand with that is the Modification Integrity Guard. This guard simply refuses to let an agent drop its own safety constraints. If a goal constraint is flagged as integrity critical, this guard strictly forbids demoting it to non-critical. So the crucial point is that this effectively enforces the ironclad contract we established way back in version 0.4. It stops an agent from deciding that the quickest way to achieve a goal is to just delete the safety rules binding it. No shortcuts allowed.
And finally, Section 5, the architecture's core, 5 durable principles.
Let's anchor this entire library in the core architectural truths that we formalized in the 0.9 release. These are the 5 durable principles of the whole project. Number 1, anomaly lane integrity, keeping our error signals typed and clean. 2, two-axis self-trust, never blending competence with integrity. 3, the goal creativity envelope, bounding motivation with pure functions. 4, goal interrogability, always being able to trace a goal's lineage. And 5, defensive guard discipline, forcing exogenous evidence for success. By cementing these 5 principles, we guarantee that the typed surface rules outlast any single code contributor. These aren't just guidelines, they are the permanent blueprint.
I want to leave you with a final, provocative thought to take back to your own development teams. If an autonomous agent relies on its own untyped cognition to monitor its own errors, who is really watching the system? By building a deterministic, dependency-light witness substrate like Sakshi, you ensure that you are the one watching the system, not the machine just hallucinating in a vacuum. Thank you so much for joining me in this explainer today. Keep building stable systems, and I'll catch you in the next one.